Good morning, my name is Manuel Zarzo, and here in this Unit 7 about analysis of variance, today I'm going to explain ANOVA in the case of three factors. Okay, so I am going to present the following experiment. Let's imagine that we have one experiment that is carried out to determine the optimum conditions in order to maximize the quality parameter in a chemical product. So imagine that we have three experimental factors that are considered. Like the type of catalyst, we can choose one or two that we will call type A or type B. Also, we have two different kinds of suppliers of the raw material that we can choose. We can choose either as supplier 1 or supplier 2. And also we can decide about to work with 70 degrees or 80 degrees in the temperature about the reaction. Okay, so this is the matrix of the design, how it is organized. So we have tested the two types of catalysts, which are combined with the two different kind of suppliers, and also combined with the two types of temperature. We have then two catalysts multiplied by two suppliers, and then multiplied by two temperatures. This is the 8 trials, the 8 experimental trials in this complete design. Okay, so imagine that we run every one of these trials, and imagine that this is the response that we get experimentally. So the target is to analyze this with ANOVA, and let's see what happens. So the target or the goal of this experiment is to determine the optimum operative conditions that should be adopted to maximize the final quality. Okay. Well, so one option is to choose the highest value in our experiment. So we have obtained that the value 23 was the highest, and it was obtained with catalyst B, supplier 1, and temperature 80. So can we say that these are the optimum operative conditions that we should choose from now on in order to get, on average, the highest values? Well, the answer is not necessarily. Okay. Only this would be true in case of the effects of all factors would be statistically significant, but this may not be necessarily true. So we have to analyze the data with ANOVA. Okay, so let's go. Then these are the data obtained with the first catalyst and the second catalyst. Then the average is the best prediction. So we put first, we put observed value minus the grand mean squared. If we sum these values, we have the total sum of squares. And then the best prediction, as I was saying, is the average. So for these four values, their average is 14.5. So this is the best prediction. And then for the other four values, the prediction is 17.5. So we put every value predicted minus the grand mean squared, we sum, and then we get this sum of squares for this factor called catalyst. Okay, great. And so we do the same for supplier. So we arrange the values so that these four values correspond to the first supplier, and these four values correspond to the second supplier. So again, we make the average. So this average of these four values will be the best prediction, and the average of these four values, which is 13.25, is the best prediction. So now we predict the value minus the grand mean squared, we sum, and we get the sum of squares for supplier, which is the next factor. And then we have temperature. So we have two values here for temperature 70, two values here for temperature 70 also. Okay, so if we make the average of 15, 20, 16, and 14, the average is 16.25, and for the rest of four values, the average is 15.75. So we make then predicted value minus the grand mean squared, then we sum, and finally we get this sum of squares for temperature. Well, with this information, we can make the ANOVA table. So here, we can start by filling out the table. Okay, so this is an important set issue, the ANOVA table that I will explain in different examples. So from now on, we have obtained this information, the total sum of squares and the sum of squares of the three factors. So then, by difference, firstly, we compute the residual sum of squares. And then we go to the degrees of freedom. The total degrees of freedom is the total number of values minus 1. So here in this experiment, we have 8 values, so 8 minus 1 is 7. And then for the factor, the degrees of freedom for the factor, it is number of variance minus 1. So we have 2 types of catalysts, 2 types of suppliers, and 2 types of temperature. So 2 minus 1 is 1. And then by difference, we compute the degrees of freedom for the residual, which is 7 minus 3, it's 4. Well, important, 4 is the minimum value for the ANOVA. If we have less than 4 values, the results are not reliable. So one important thing is that at least we should have 4 degrees of freedom here. Then we divide the sum of squares by the degrees of freedom, and we have the mean squares for every 3 factors, and then for the residual. And then we divide the mean squares of catalyst by the residual mean squares, and we get the F ratio. And then we divide the mean squares of supplier by the residual mean squares, and we have the F ratio for supplier, and the same for temperature. And then we have to check about the range of frequent values for this distribution. So in the 3 cases, the F ratio was obtained by dividing the mean square with 1 degree of freedom by the residual, which has 4 degrees of freedom. So we have to go to the Fisher's distribution with 1 degree of freedom in the denominator and 4 in the denominator. So if we consider alpha 5%, which is the most frequent value, so the critical value is 7.71. So we have to compare these values. So, and then we have that in the 3 cases, the F ratio is less than the critical value. So it means that these are like frequent values for this distribution. So we don't have enough evidence to reject the null hypothesis. Okay, but what happens here is that this value is not too far away from the critical value. And remember that in this case, we just have 4 degrees of freedom, which is not quite much. So now what we are going to do is to repeat the same ANOVA table, but removing this row, because the F ratio is very small, and also removing the first row, because the F ratio also is small. Okay, so again, we fill out this ANOVA table. Sum of squares for supplier, the total. So again, by difference, we compute the residual sum of squares. The degrees of freedom again is 1 for supplier, 7 for the total. By difference, we now have 6. So now we have increased from 4 to 6, which is good. I mean, so the higher the number of residual degrees of freedom, the more powerful is the test to find statistically significant differences. So now, again, we divide the sum of squares by the degrees of freedom, we get the mean squares, and then by dividing these mean squares by the residual mean squares, we get the F ratio. So now, in this case, we'll have to go to the Fisher's table with 1 degree of freedom in the numerator and 6 in the denominator, and then the critical value is 5.99. And then, interestingly, in this case, the F ratio is higher than the critical value. So it means that this value is not frequent for this distribution, so we have evidence to reject the null hypothesis. And this is important. Okay, so we conclude that factor supplier is statistically significant. So what would be the optimum conditions to maximize the response variable? To use supplier 1. So we have to choose between S1 or S2. In this case, we choose S1 because on average, as I have explained in the previous slides, we were obtaining a higher value with this first supplier. And then for temperature, as this factor was not significant, it doesn't matter to choose 70 or 80. Probably in this case, we will choose 70 because we don't need so much power for heating. So probably 70 would be better, but from the data, we don't have information to say which one is better. And then regarding the catalyst, we can choose either A or B. So we will choose the cheapest or the one which is more convenient for some technical reason. Okay, and then this is the average of the 4 values with the first supplier. So if from now on we work with this for Supplier, this is the best prediction that we can give as optimum operative conditions. Well, next, we should check that residuals follow a normal distribution, which means that we don't have outliers affecting the results. We can check this condition, and actually it turns out to be correct. And also, finally, there's something else that we should check. We should check that the interaction between supplier and temperature, or the interaction between supplier and catalyst, is not statistically significant. This is something that I will explain in the next videos. Okay, what is the interaction? Well, this is something that will be explained in the next video. Thank you for your attention.